Hi, welcome to module 21 of week 4. In this module we are going to look at a demonstration of Verilog once more. So, and when I do that I want to show some of the principles in writing Verilog code. Particularly I am going to introduce you to a new kind of statement called assignment statement, and I am also going to show you how to do what is called hierarchical design. So, let us start with this basic problem. So, let us say I want to design a 2 to 1 multiplexer, and for this 2 to 1 multiplexer I want to write Verilog code. So, let us look at the picture here. So, what I want is I want a circuit which will behave as a 2 to 1 mux. So, it is supposed to take 3 inputs A, B and select, and it has to give one output called out, and internally I want a 2 to 1 multiplexer. And to be more specific, I want this. So, when select is 0 I want A to be in the output, and when select is 1 I want to be B to be passed on to the output. So, this is the hardware that I have in mind, and I want to be able to describe that. So, one thing you can do for this this particular multiplexer is, you know that a multiplexer can be implemented using AND, OR and inverters. So, you can go and do that. So, we already discussed this in the last week's Verilog demonstration. So, we saw how to use the primitive gates or primitive data types. So, we looked at AND, OR and so on. We can use those primitive structures and write what is called a structural description for this. So, a structural description would essentially say, oh, I want one AND gate which takes A, another AND gate which will take B as input, and you have a select line. You would imply some structure like this. So, once you have a structure like this, right, you will have 4 Verilog lines, let us say 1 for OR gate, 2 for these AND gates and 1 for the inverter. So, that is completely possible, but I am going to do something different for this class. So, we are going to see how to do this Verilog description in a slightly different way, and the first thing we are going to look at is what is called an assign statement. So, the statement is called an assign statement, and I am going to go to this website edaplayground.com and show you the demo of how to write Verilog code for this, and I will also write a test bench to go with it. So, I am going to do this on edaplayground.com. I am already logged in. So, I am designing a circuit called 2 to 1 mux. I am going to call it mux 2 1, and I know that there is one output and there are 3 inputs. So, one thing that Verilog allows you to do is to directly say whether it is output or input when you describe the module itself. So, I am choosing to do that now. So, I need one output and 3 inputs, namely input select, input A and input B. So, unlike the last class where we did we wrote only the names and then we explicitly said inputs or outputs in separate line, I have done this in the modules line description itself. And I generally have this habit of putting module and end module, so that I know I do not have to go and remember to do it later. As and when I create a block of code, I also put the corresponding matching description at the end. So, now I am going to describe the output. So, at this point if we did what is called structural description of multiplexer, what we would have done is we would have instantiated the 2 AND gates, 1 OR gate and 1 inverter and so on, and wired all of them up. But Verilog, as I mentioned earlier, can work at different levels of abstraction. So, I am going to write it in another level of abstraction where we can actually write the Boolean equations directly. So, for example, we know that output is actually select bar into A plus select into B. This is what we wanted from the multiplexer. So, there is a way to do that directly in Verilog. So, I am going to do that now. So, select bar into A. So, I will come to the syntax in a little while, or select into B. So, if you look at this statement, this is just a Boolean equation. So, I am following the syntax of Verilog, and Verilog syntax is very similar to the syntax that C and C++ has. So, this ampersand in Verilog is a bitwise AND. This pipe symbol that I have here, which you can see right above the enter button, right, that is bitwise OR, and this exclamation symbol which is along with the one key, that's not. So you have not, and or. So if you know how to write expressions in C, this is very similar. The only key thing you have to remember is this is a bitwise and this is a bitwise or. So we have only one ampersand and one pipe symbol. So it will be nice if we can actually write an equation like this. If we know an equation, it will be nice if Verilog can actually let us do something like this directly. In fact, Verilog does that, and the way to do that is Verilog allows us to do something called an assign statement. So there is a keyword called assign. You can notice that the assign statement actually became the keyword assign changed color. So you can say assign output equals not of select and A or select and B. So this is select bar into A plus select into B. So usually if, I put parentheses to explicitly say this is one group of operation and this is one group of operation. So you do not have to do that once you know what is the precedence of ampersand over or and so on, but this is a very safe way to do it. So let us say I have a design in hand now, it is as simple as that, that is it, no instantiations, nothing. So what we have done is we have taken the Boolean equation required for output in terms of select A and input, and we have directly written that as a Boolean equation. So it is a very simple design and it is okay to do that. Now I am going to write a test bench for this. So for the test bench I am going to call that mux21 underscore test bench. So I already said that I use this convention called underscore TB to indicate that it is a test bench for this particular module. So if I am testing an XOR gate, I would have put XOR underscore TB and so on. So now what I am going to do is I need descriptions, right. So I need a mechanism by which this whole setup is going to be inside a test bench. So just like what we did in the previous video, we need to be able to give A, B and select as inputs, and we need to be able to observe out, which is the output signal. So as I did in the previous lecture, I am going to declare 3 regs. We will see what a reg is later, but we will use 3 regs wire A, B and select, so A, B and select, and I am going to declare a wire called out. So these are the things which are going to be in the test bench, and we need a mechanism by which the test bench gets connected to the actual module, right. So the design under test. So for the design under test, we know that the design under test, the type of the design is called mux21, and I am going to give a name for that called DUT1. The order of the pins were output select A and B. So at this point what we have is, you can imagine that we picked up a breadboard, we put a multiplexer in it, and we have not connected any wires or anything yet. So that is what we have so far. So we have connected all the, so we have put the breadboard, we have put the multiplexer chip in it, we still have to say, oh, this is the A pin and it has to connect to this power supply, I am going to iterate over all values, all these things, right, we will have to do. So I am going to write an initial statement for that. So I have an initial statement. So this initial statement, in this initial statement I am going to write a loop which will iterate over all the possible combinations of select A and B. So just like what we did in the previous example, select A and B will have 8 different combinations. So I am going to write that for int I equals 0, I less than 8, I equals I plus 1, right. So this is the for loop, begin, end, right. So because of the size of the font that I am choosing and so on, so I have done this so that you can see it in the video clearly, but if you are sitting in front of a computer, you will probably have a much smaller font size. This begin would come into the same line itself. So I can show you how it will look. So it would look like this, whereas, so if I have a properly sized window, it would look nice. So the platform is quite nice, but I have chosen a bigger font so that you can see what we are doing, right. So let me work with this font now. So we have the loop running, and already I mentioned this in the last class. If I want to give a vector of inputs, right, so select A and B are 3 different inputs, and when I say is assigned to select A and B, right, you have select A and B on the left side. So I gets values from 0 0 0 to 1 1 1 and these specific bits are assigned to the left side. So this is something that you have already seen. I am going to do something slightly more this time. So I also said I am going to give this every 5 time units, I will put that in. So till this is very similar to what we did in the previous test bench. On top of this I am going to do a few more things. So one thing that we do for test bench is that we can always go and visually see what the output is, we can see what the waveform is and so on, but sometimes it is also a good idea to actually know that this is what I am expecting from the design and am I getting the correct output or not. So when we write the test bench modules, so this is not something that you get from your breadboard, your oscilloscope kind of setup. So you have to inspect, as a human being you have to go and see what the oscilloscope has and you have to check whether the outputs are correct or not. You will have to do those things, or you have to inspect the LED that you have connected and whatnot. But in Verilog, since you are writing a program, you can also programmatically check whether the output that you are getting is correct or not. So I am going to do that right now. So I know that if select is 1, so we will come to the syntax later, if select is 1 and if output is not equal to A, let us say I wrote the design, now the design is actually correct, but it is possible that I make some mistakes, or if you go and write your own design you may make a mistake. So what I am going to do is, if select is if select is 0 and output is not equal to A, I am going to declare, so I am going to do something, I am going to say that there is some failure, there is something that is happening. So I am supposed to get A, whatever A is whenever select is 0, however if for whatever reason it fails, I am going to indicate that there is a failure. The same thing can happen if select is 1, right, and output is not equal to B, this is also a problem, right. So I want to say that this is also a place where I want to indicate that it is a failure. If it passes, if all these things pass, I am going to say that it is passing. So I am going to do a few things in a little while. So again, if you want to see the structure, this is how the structure looks like. So this is how the structure looks like. There is a if statement, there is a else if statement and a else statement. If you look at what is happening in fail and pass and so on, it looks like it is a function call that we are making. It is in fact actually a function call. So on the right side we have our design. In the test bench we are going to use the full power of writing software as though you do it in a programming language. So when you write the design description, you generally do not write functions and so on, but when you are testing it, your test bed or the test bench is essentially a piece of software by itself. It is not implying any hardware directly. It is not that we want to synthesize an oscilloscope or we want to get a voltage supply out of this. If we give this voltage supply and if we have to see the waveforms, what is going to happen? That is what we are doing in this whole business of simulation, right. So you can use the whole power of software programming inside the test bench. Anything that you do in test bench which uses traditional software techniques is actually welcome and it is good to have. So what I have done is, I have put a series of if else statements and there is a for loop and this is the overall structure. So now let me show you what some of these things mean. So if select equals 1 apostrophe B0, this apostrophe is the signal or is the key next to the enter key, right. This is the close quote, close single quote. 1 tick is what Verilog folks call it, 1 tick B0 and out is not equal to A, then I know that there is something wrong in the design. So if that was true, however it is possible that when select is 1, somehow out was not equal to B. So one of the cases could have been wrong. If either of these things happen, I know that there is something wrong in my design. If this is correct, then everything is correct, I can pass this test case, right. This test case is correct. So what I am going to do is I am going to put this inside an initial block, and what this will do is it will iterate, the for loop will iterate from 0 to 7, it will stop when it is 8. So 0 to 7, it assigns I to select a comma b, select comma a comma b, and you can imagine this as signals that are being fed into the device, and you will get output from the device. In this case the device is mux21. So let us assume that there is 5 units of time that I have given for the mux to respond back. That is what this hash 5 means. I am giving some unit of time for the hardware to respond back. In this case it is all in software, but in reality you have to wait for the output to change. You cannot give an input and instantaneously expect the output to be ready. So we are mimicking that by putting a hash 5, and these 3 lines what it is doing is we are checking whether the outputs are correct or not. So this is a very quick and easy way to do this. For example, if you had written a design, let us say you designed a very complicated circuit to take 2 numbers and multiply and so on, right. You have your design and that is on one side. On the other side, if you want to check whether the results are correct or not, you could do A into B, for instance, right. So A into B does not imply any hardware at all. You know that it is a multiplier. How to design a multiplier, that is not clear from it. Whereas when we write design descriptions, it is usually very clear to us what we really want from the Verilog description. So far we are there, and I am going to write the what are called tasks. So I am going to write one task called fail, and this task is supposed to take care of the failing condition. So when will we call this function fail? If one of these if conditions were correct. So somehow the output was not A when the input was 0, when select input was 0, or the output was not B when the select input was 1, then we have a problem, right. So I am going to say that there is a problem in these cases. So I am going to print something to the screen saying display when select A B, right. I am going to write it like in English, when select A B is these 3 values. So this is similar to printf statement. You can see that it is resembling the format of printf. When select A B is this, output equal to this is wrong, right. I am going to write something like this, right. And what are the different things? It is just like in printf statement for C. So the first part is a format specifier and the second part is a actual parameters. So when select comma A comma B is select comma A comma B, output equal to whatever output we got is wrong. It is okay to say it is wrong here because you will call this function only when the output is wrong. You will not call this function when the output is correct, and this takes care of the fact that there is a problem. And if there is any problem in your design, right, so if there is anything wrong in the design at all, ideally what I want is I want to just say that do not continue with the simulation anymore, there is a mistake in the design and you have to go and check it, right. So I am going to finish simulation. So what this will do is abruptly it will finish the simulation, it will not even go to the next iteration required for running this program. So I will abruptly finish. Similarly for pass, so what I am going to do is I am going to say that if it is pass, which means for each of the inputs, in each of the combinations of inputs, if it is correct, right, I am going to put this statement. So I will copy from the previous one, I will say that out equal to this, and that is it. So I will not say it is wrong, the output is actually correct. So whenever I say output equal to that, we will assume that it is correct, that is all. So if it is wrong, I will explicitly say it is wrong, if it is correct, I will just print it out. And in this place I am not going to put $finish, because if one input combination, if the output is correct, I still have to check all the input combinations. So I should not finish them, I should check all the input combinations, right. If it fails, I am going to get out immediately and say that there is something wrong in the design, but if it is passing, then I am going to let it pass, let it go till the very end. And let us now go back to this initial block. So what would happen? You would run from 0 to 7, and every time you can think about it as there were 3 inputs that were given, you waited for some time, the hardware gave the output, you check the output, if the output is correct you pass, so which means you this will print something on the screen and it will go to the next iteration. If it fails, it will call this task called fail, it displays what is wrong in your design and then finishes the simulation. So at some point, if for all the input combinations, if everything passed, you will get out of this for loop, so the for loop would terminate. At this point I can actually say that all the test cases passed. So I can be happy about this, right? All test cases passed and now I am ready to finish, right? So this is the overall setup. So what we are going to do is, so I'll just reduce the font size again so that you can see the structure, the overall structure. So even if you don't see the actual contents, you can see that there is an initial statement here which takes care of giving the various input combinations. It also checks whether the output produced is correct or not, and if the output produced is incorrect, we are going to call this function. If the output produced is correct, we are going to call this function. So far we are okay. I am going to now run this. So I am going to save and run it. So what happens when you run is, it comes in the bottom. Let us see what is happening. So I did not pick the correct simulators and so on, let me do that, I am sorry. So we will pick system Verilog and I am going to pick for tools and simulators, I am going to pick iVerilog 0.10.0. So right now I do not want the waveforms, so I will go and save it and run. So sometimes the website has sometimes it can have issues. If you see that there is nothing which has changed in the output, just go and run it once more, you will see that it will become a blank screen and eventually you will see the output again, right. Now let us see this. So when so this design is actually correct, it says when select a b is 0 0 0, output is blank, then there are several things which are all blanks. So it looks like I did something which is incorrect. So let me go and see what it is. So I said when select a, b is these 3 values, output equal to %s. So %s is not a valid specifier, so I should have put %b. So %b means print it as a bit. So we have seen D and other things in C programming, right. So %b means print it as a bit. So that is a mistake that I had done. So I have corrected that mistake and I am going to run it again. Let me run it once more. Now let us see the output, right. So let us check, pick a line and check it. When select a, b equal to 0 1 1. So when select equals to 0, a equals to 1 and b equals to 1, output is 1. So which is in fact correct. Let us check this line. When select is 1, a is 1 and b is 0, right. So we know that it's select bar into a plus select into b, so we should be selecting b, so b is 0, so output is 0. This seems to be correct. So let me show what would happen if I make a small mistake. So let us say by mistake I forgot this not condition, right. So I put select and a or select and b. So let us say I made that mistake. Let us say you wrote a design like that. If I save it and run it, I am expecting something wrong, correct. So this did not run, let me run it once more. Okay. So let us see the output now. So when select a, b is 0 0 0, output is 0. When select a, b is 0 0 1, right. So what we are expecting is when select is 0 and when a is 0 and b is 1, since select is 0, you are still supposed to get 0 out of it, so that is okay, right. So when select is 0, you are printing a. Let us look at this line. When select is 0 and a is, so let us see this, select is 0, a is 1 and b is 0, we should be outputting 1. However, the output is coming out as 0 because we made a mistake here. As soon as in the sequence of input combinations we find out an error, so what would happen is in this for loop you have I equal to 0, for I equal to 0 everything passes, for I equal to 1 again it passes, for I equal to 2 however the design seems to give an incorrect result, right. As soon as you see something incorrect, this is a very conservative way of programming. As soon as you see something incorrect, say that it is incorrect, unless you go and fix the design you should not allow it to continue. So this is the setup. So I will go back and put select there and that is it. So that is basically the design. So now I know that this design is correct, and if you want you can go and open the waveform and whatnot, right. So this is a very simple example. In this case I didn't put any statements for waveform viewing and so on. I just wanted to illustrate that you can actually do something called automatic checking right inside the design. So I have done that now. Instead of looking at the printout and manually checking one after the other, I know that when select is 0 output must be A, when select is 1 output must be B. I am explicitly checking it in the program. So this is something you must have also observed in the test bench that I provided you for the XOR gate. So in quiz 3 at the end of it I specified a practice problem. The test bench there is also something that actually uses the same technique. Okay. So now let me do one more design. So in this design I want to show you something which is equivalent to what is called instantiation. So now let us say my design problem, let us look at the picture. Let us say the design problem is design of a 4-to-1 mux. So when we design a 4-to-1 mux, the test cases are like this. So this is the setup. So we will have two inputs, select 1 and select 0. These are the two inputs, and these are the select lines, and I have 4 inputs, proper inputs A, B, C and D. There is a single output, and the select 1 and select not, if they are 0, 0, then output should be equal to A. Then if these two are 0, 1, the output must be equal to B and so on. This is what I want from the Verilog design. And so I could go and write equations for this. I can go and write out equals combination of select 1 and select not with A, B, C and D. That is one way to do it. I already demonstrated that. I suggest that you actually go and try it yourself. Now I am going to show something else which is slightly different. So I am trying to show different ways of writing Verilog for a design problem. Let us say I want to do this in Verilog, but I want to use 2-to-1 muxes, right. So I have 2-to-1 muxes. This is a valid circuit for a 4-to-1 mux designed using a 2-to-1 mux. So you give A and B inputs to a 2-to-1 mux, C and D inputs to another 2-to-1 mux, and give select 0 as the select line. This is not select 1, this is select 0. So this one is correct. So this is not a mistake, it is select 0. You give select 0 as the inputs as the select line to these two muxes. So now you know that if select 0 is 0, it will pick A from here and it will pick C from here, which is what we want, right. You look at this, if select 0 is 0, then either A or C should come. If select 0 is 1, which means the last 2 bit are 1, either B or D should go to the output. That is what we are doing with this part of the circuit. So when select 0, so we give the same select lines here. So if select 0 is 0, A and C will appear here. If select 0 is 1, B and D will appear here in these places. Then we have another 2-to-1 mux. This 2-to-1 mux is taking select 1 as the select line, and it will, if it is A here, it would be C here, if it is B here, it will pick D here, and it will pick one of those and pass it to the output. So now I already showed this in an earlier class that this is actually a valid implementation for a 4-to-1 mux. So if I want to design a circuit like this, which actually uses 3 2-to-1 muxes to design a 4-to-1 mux, so I need to be able to do that. So imagine I ask you to build a circuit in a lab where you have 3 2-to-1 multiplexers. I want you to put it in the breadboard and so on. Then that is what we are trying to simulate. So when you do this, right, usually you go and give names to the multiplexers here. So for example, I am going to call this multiplexer M1, this multiplexer M2 and this multiplexer M3. So the reason why we want names for that is we want to be able to refer to them by names and say that multiplexer M1's inputs are A and B, multiplexer M3's inputs are 2 intermediate wires and so on, right. So, so far if I look at it as a black box, it is taking A, B, C, D, select 0 and select 1 as inputs, it is giving out as an output. Internally I could I have some structure. So again I am going to do something more, I am going to, I will need a wire for this, so I will call these temp 1 and temp 2. So let us say this is a circuit that you will draw, right. If I ask you to do it on a piece of paper, you will do this in a circuit. So what I am going to do now is I am going to write a Verilog module for this. So let me open a new window. In this window I am going to write the Verilog module. So what I am going to design, so let me just make the font sizes much bigger. So as I mentioned earlier, I want a 2 to 1 mux which has to be instantiated, and we want a 4 to 1 mux out of that. So the first thing I should be able to do then is I should first of all need a description for 2 to 1 mux. So I can always go back and pick it up from the other design there, which I will do now. So I already had a description for the 2 to 1 mux. I am going to copy that. I am going to copy that. So the 2 to 1 mux is still using a Boolean equation, right? It's as it was before. However, for designing the 4 to 1 mux, I am going to do something else. So I am going to design a 4 to 1 mux. This 4 to 1 mux will give one output called out, right? It was as it was before, and it's supposed to do a few other things. It's supposed to take 2 inputs, select 1 and select 2, and it's also supposed to take 4 other inputs, A, B, C and D, right. So this takes care of the black box description. So if you look at it as a black box, it has 4 regular inputs, 2 select inputs and 1 output. We have this. What we need now is we need a way to describe the wires that we had and the descriptions that we had. So I said we already need 2 wires, temp 1 and temp 2, right. I'll declare them now. So what we have is we have a 2 to 1 description, mux description for 2 to 1. I am going to design 4 to 1 mux using 2 to 1 muxes. So let us see how to do that. To do that, so I need to do what is called instantiation. So we in the primitives I said this is equivalent to pulling up gates and so on, right, but mux21 is not a primitive. We designed it right now, right. We designed it right now. We need a mechanism to say that I want a mux21 called M1 which will take select 0, A and B as inputs and give temp 1 as the output. So what will this statement do? So the meaning of this statement is I want a DUT, I want a device called M1. This device is of the type mux21, it is a 2 to 1 multiplexer, and in the 2 to 1 multiplexer I am going to take my inputs A and B and select 0, pass it as inputs to the 2 to 1 multiplexer. Whatever it is giving as output, I am going to call that temp 1, and this is a wire that is currently dangling. So if you go back to the picture, what we have is we have taken A of the 4 to 1 mux, given it as input to one 2 to 1 mux, and we have taken B of the 4 to 1 mux, given it as another input to the 2 to 1 mux, and the select 0 is given as the select line, right, and the output of that is called temp 1. We called this gate M1. That is what we have so far. Now I need another 2 to 1 mux. So Verilog does not stop you from doing this. So what we have done is we have done what is called instantiation, and instantiation means I have a particular hardware object, in this case it is a 2 to 1 mux, and I have picked up one copy of it. So I bought one mux21, let us say, right. So the first one I have is called M1, the second one I have is called M2, and I am going to declare so to that mux these are the inputs. It will take the same select line, it takes C and D as the inputs and it gives you temp 2, right. So temp 2 is the other wire. Now we have 2 wires and this has to be connected to the third wire, the third multiplexer. So the third multiplexer gives the circuits output as a black box. Out is the output of the 4 to 1 mux, and what is the final 2 to 1 mux supposed to do? So let us look at the picture again. So M3 takes select 1 as the input and temp 1 and temp 2 as the two inputs, select 1 as the control input or the select input, and the output is driven to out directly, which is what I am going to do now. So we have out, which is the output, you can see that here. The select line is supposed to be SEL1 now, and we are passing on temp 1 and temp 2 as the other two input lines. So the order in which we have given things have to be careful. So A and B are given in that order, C and D are given in that order, and temp 1 and temp 2 are given in this order. There is a reason for that, because unless you do this, if you mix up A and B, then your 4 to 1 description would be incorrect. So we want, when select 1 is 0 and select 0 is 0, we want A, and when select 1 is 0 and select 0 is 1, we want B, and so on. So now this is a design description for a 4 to 1 mux. So what I am going to do is, I am going to provide you the code for the 2 to 1 mux, and I will give you the test bench for it. For this one also I will give you a test bench. I suggest that you go and take this and write the program yourself, just like what you did for homework in quiz 3. At the end I gave a practice problem. Just like that, for week 4 also you do a few practice problems. I will give these Verilog codes, as well as I will post some new problems, and you can go and write it yourself. So for this, the test bench that I am going to give is very similar to the test bench that I wrote for mux 2.1. So I am going to instantiate this mux 4.1 into another test bench, and in that test bench I will pass various inputs and so on. I will get the outputs, I will compare the outputs, and I will see whether it is expected or not, which is what I am going to do for the, I will put that test bench code on the platform, and you can see these 4 Verilog files in the platform. You first get familiar with running it and so on. So again, even if you do not understand what the test bench is doing, at least the design description must be clear to you. So we described what is called a mux 2.1, and we used 3 copies of this mux 2.1 to design a mux 4.1 or a 4 to 1 multiplexer. That is what I want to capture, want you to capture. So far we have seen 3 different kinds of statements. We have seen something called the primitive gates. So we said and, or, and so on, those were primitive things. Then we saw something called an assign statement. An assign statement usually appears in the module directly, and you have something on the left side equal to some equation on the right side. And finally we also saw how to pick various components that are already present, which you have designed, and how to wire them up together. So these are actually 3 different levels of abstraction for Verilog design. So I will leave the video at this point. So at this point you have the basic infrastructure to run Verilog, and I suggest that you go and take the Verilog files and run it yourself and check whether the outputs are as expected or not. So if you want to try it, go and write your own mux 4.1, right. So you can delete the mux 2.1 and you can write a Boolean equation for mux 4.1 and check whether your Boolean expressions are correct or not, right. So this brings me to the end of this video. Thank you very much.